You might never forget how to ride a bike, but what makes one bike faster than another? Take an ordinary racing cycle. We all know about that. Pedal it and it goes. After all, it's a machine. We apply force to the pedals, result, motion. But there's more to it than that. What happens if we stop applying the force? How far will it go? And why does it stop without you using the brakes? Think bicycling science and maybe go cycling crazy. Say we applied a limited force to the bike, a single turn of the pedals, or 2 turns, or even 3. Each time the bike moves forwards. It travels a certain distance, then comes to a halt. More force, the bike travels further, but it still stops. So what's stopping it? Cycling's certainly not effortless. You have to apply a force to start moving and to keep moving. So there must be another force acting in the opposite direction. Maybe more than one. What are these forces resisting your attempts to ride the open roads? Let's start with the bike itself. There's always someone who'll tell you cycling's the most efficient form of transport, very reassuring and environmentally sound. But should you believe them? Machines are meant to do something useful, but how do you tell they're doing it well? Efficiency. Take a water mill, another mechanism of gears and wheels. Like any machine, it has a power source. Here it's the flowing water which applies a force to turn the wheel, which eventually turns the grinding stones that mill the flour. That's useful work, and that's what we're interested in. But how efficient is it? That depends on other forces within the mechanism, forces resisting the motion of the wheels, gears, and so on. More resistance, less useful work, less efficient. Same principles apply to a bike. But how do we measure the efficiency of a machine? We can't just take it for granted. Might as well do it here as anywhere. I've never seen a water-powered bike, but we do need something to apply a force to the pedals. Take a cyclist, saddle up and start him pedalling. No special bike, the measurements are as near as possible to normal cycling, except the front wheel has been removed so he can't ride off into the sunset. Not that that looks very likely. The computer monitors his progress on a 3-kilometre test. But one big difference from out on the road, no wind. Well, that should make it easier. No need to train out in the rain if you've got one of these. In fact, no road at all. The rear wheel turns a roller. That's the useful work the cyclist is doing, the work that will be getting him home or to the finishing line, the output of the machine. And we know where the input comes from, the guy in the saddle. Willing subject, experimental setup, unusual environment. But do we know everything we need to measure efficiency? Not quite. It's not the amount of work done that matters to a cyclist, it's the rate at which you do it. Power. Imagine cycling up a hill. Fast or slow, it's the same height, same amount of work. But that attitude won't win you a hill trial. You've got to have the power. So, is a bike efficient? We need some figures. Power input and power output. But where can we measure them? Power output, that's fairly easy. Measure the power from the rear wheel that goes into turning the roller. Useful information to a racing cyclist, It tells him how fast he's going. Our cyclist had a power output of 270 watts. But now for the tricky bit, measuring the power input. First question, where? Second question, how? The where is pretty obvious, but power is the rate of doing work. Our cyclist is pedalling at 1 revolution per second. That's handy. So how much work is he doing during each rotation? Well, think about lifting a weight. Work is the force you apply multiplied by the distance you move it through. We know the length of the pedal, so we can work out how far it travels each revolution, which is also each second. With a force transducer in the pedal, we can measure the force. Interesting. There's always some force on the pedal, but it varies during the movement. No worries. Produce an average force. But hang on, I can hear you saying. There are 2 pedals. No problem. 2 pedals, double the force. So that's the force applied. Multiply that by the distance each second, and you get the input power. More or less than you expected? Power in, 300, but power out, 270. That gives us an efficiency of 95%. Very efficient. Only 5% of the input power is lost in the mechanism. But if cycles are so efficient, why is cycling such hard work? When it comes to the forces stopping a bike, resistance in the machine doesn't seem that important. So why does the bike stop? Back out in the track, it looks fairly easy. But to keep a bike going at a constant speed, you have to keep pedaling. That provides a large force acting in this direction. But you don't go any faster. Maybe we've missed something. An equal force acting in the opposite direction, resisting the movement? But what could be producing it? Friction, the force of the road and the wheels which resist the movement of the bike. But what would happen to a bike if there wasn't any friction? Would it keep moving or stop? Watch this. What starts the ball moving? The force due to gravity. But what stops it? The force of friction between the ball and the rail. Imagine there was no force of friction. The motion never stops. But what if this imaginary friction-free track wasn't looped? Gravity still sets the ball in motion, but no friction, no force opposing the moving ball. It just keeps rolling along. Hard to imagine a friction-free world, but not all surfaces are the same. Try cycling on ice, or on a newly made road. Rougher or smoother than the cycle track? More or less friction? Resistance due to the bike, resistance due to friction with the road. Is that the whole story? No chance. Ever notice that you're always cycling into the wind? But on some bikes, it seems easier than others. Same road, same friction. So what's going on? Different bikes, different shapes, different sizes. But how can that affect the forces on a bike? It's often called air resistance, but it's actually a force. The force needed to push the bike and rider through the air. In a wind tunnel, we can measure the force on different objects. They don't move, but the air does. Take a simple shape, attach it to a strain gauge. It's then suspended in the mouth of the tunnel. When the air is still, there's no force. But air moving through the tunnel pushes the block backwards, bending the strain gauge. This gives us a reading which we can calibrate in newtons. So is it size or shape that matters? First, 3 blocks, same shape, different sizes. Bigger block, more force. But only the area facing directly into the moving air is different. Halve this cross-sectional area, and you halve the force due to air resistance. But what happens if you speed up the air in the wind tunnel? What does that tell you? So, smaller bikes, faster bikes. Shape doesn't make a difference. Or does it? This bike isn't as fast as this one, but they've got the same cross-sectional area. Back to the wind tunnel. This time different shaped blocks, but the same size. But why does shape make such a big difference? Watch this. The air flowing past the bike is very turbulent in some places, particularly around the pedals. Take a closer look. The more disturbed the airflow, the greater the force due to air resistance. But watch what happens when the cyclist fits a nose cone in front of the pedals. Smoother airflow, less resistance. This is streamlining. An anorak? No. But you can take streamlining even further, if you don't mind some odd looks. So how would you design the world's fastest bike? Efficient mechanism? Obviously. Fit rider? Absolutely. Very thin, all-enveloping body and a streamlined shape? You bet. Compare this bike with a flat silhouette of the same area. And if you get it all right, maybe you can challenge this world record holder. but you have to beat 74 kilometers in 1 hour. Not bad for pedal power. There's just one problem with this design: stopping. So cycling's all about forces and motion. If you apply a force greater than all the forces of resistance, you go faster. When there's a balance, you maintain a constant velocity. But there are times when you want to increase the resistance to your movement. Fast. Friction's not always a bad thing. But if you do want to use the brakes, how quickly can you stop? Watch this. These two lines are 2 meters apart. We can calculate the cyclist's velocity immediately before she puts on the brakes and measure the stopping distance. First velocity, a snail's pace of 3 meters per second. Stopping distance, a very short 2.8 meters. But as the velocity increases, the stopping distance increases more. What does that tell you about braking? Slam on the brakes too hard and you'd lock the wheels. You have to apply a constant force to avoid that. A constant force? How does that affect the motion of the bike? On a distance time graph, we can see it certainly looks very smooth. But how is her velocity changing? Stop the tape every half second. You can use that to calculate her velocity in each interval. It decreases steadily. She is decelerating, the opposite of accelerating. So a constant force opposed to the direction of motion produces a constant deceleration. The rate of deceleration is the slope of the line. A very useful thing, friction, if you don't try too hard.